Okay, now what I have on the left here is just a Mathematica window, right? And so I'll leave that open. I'll seldom use it, but it's just to check some calculations here and there, all right? So for example, how do we do 1 plus 1? Well, I write it and then I press Shift and Enter at the same time, and it tells me that the answer is 2. So I can check various things here. Okay, so I'm going to write on this and talk about this document, and primarily most of the discussing will be right here, and so that's on the right hand side of your screen. But occasionally I'll go over on the left and do some calculations to check things, because we all make mistakes, right? So not bad to be able to do that. And then sometimes I want to display graphics for you too. Okay, calculus of one variable. Calculus is generally thought of as the study of rates of change of functions. It goes back to Newton and Leibniz. We each developed these tools independently, or so we are told, at about the same time. To begin our study of calculus, let's recall what a function is, and I'll present sort of 2 points of view on the definition of a function. A function is a rule, f, for sending the elements of a set x to the elements of the set y, such that f of x is uniquely defined for all x in the set x. For example, if f is a function which takes an element x of the set x and squares it, then mathematically we can denote this as follows. So over here we've got f colon x and then an arrow going to y. So what this could be seen as is f is a rule for sending the elements of the set x to the set y. Okay, and then here we see that the domain is x by definition in setting this out, and the codomain is y. All right, but the rule is explicitly given by f of x is equal to x squared. So it takes in x, what it does to it is it squares it, multiplies it by itself. All right, so occasionally though, it's useful to see a different point of view. And so for this different point of view, you could see a book by Spivak. Now I don't see that here. Oh yeah, hang on, just give me a second. All right, so here is Spivak. It's a big calculus book. I think you'd find it a bit hard, so I'm just going to use this as a reference where necessary, but I prefer you to be reading Stewart. Okay, so this is the book where I get epsilon delta proofs and examples. All right, so don't buy that one unless you are a serious mathematics student. So the book we'll primarily be using, and I'm not telling you to buy this one either, is Calculus by James Stewart. So you'll find lots of extra examples to work through, and it's good reading too. I just have a 7th edition here, but I think I have another edition around. They're not too different from one edition to another though. Okay, but most of the information will be in this document. It's just not quite as comprehensive as, say, a book by James Stewart. Okay, so let's jump back into this. So for the second point of view, and this one comes from Spivak, a function is a collection of pairs of numbers with the following property. All right, so you see these are pairs here. If a comma b and a comma c, notice the a's are the same, are both in the collection, then b equals c. All right, so you've got to have this property here for that collection to be called a function. In other words, the collection must not contain two different pairs with the same first element. All right, so whenever you have the same first element, the second element has to be different. So let's look at an example here, and you're going to write here. Okay, there's not very much space, so write small, but we don't have a lot to say about this example. Okay, so the circle. All right, so let's sketch a little circle. Now this is the unit circle of radius 1. X squared plus y squared equals 1. It's not a function. All right, why is it not a function? Well, we have root 2 on 2, comma, root 2 on 2 is a point. Is a member, let's say, or an element of the collection C, right? And C is the set of all real points satisfying x squared plus y squared equals 1. All right, but root 2 on 2 minus root 2 on 2 is also in the collection C. But we see that root 2 on 2 is not equal to minus root 2 on 2. Okay, so we conclude C is not a function. And so there would be infinitely many points on this curve C, or collection C, the set of all real points satisfying that equation. But it doesn't form a function because basically for every x value there are exactly 2 y values. All right, and so that means that this property right here, the b and the c, would not be equal. All right, but let's look at this in a little bit more detail here because I've got a Mathematica plot of this, and to do this I use contour plot. You know what, why don't I just show you right here how I do that. Contour plot, x squared plus y squared equals 1, and then when I do a contour plot I got to set an x boundary and a y boundary. So I'll go -1 to 1 for x, and y goes from -1 to 1 as well. And I'll press shift and enter. Since I've just opened it up, it takes a little while, but there's my circle. All right, and so the 2 points that we talked about in the previous example were somewhere in here and here. Okay, so this one would be root 2 on 2, root 2 on 2, and then this one down here would be same x value, root 2 on 2 minus root 2 on 2. All right, now we can draw a vertical line passing through those 2 points, and so we can see geometrically that this curve fails the vertical line test. So C fails the vertical line test. Okay, so if C were a function, then every vertical line that intersects with C must intersect with C exactly once for that C to be a function. And so here you see it intersects twice, so C cannot be a function. All right, but you can modify the definition of it to make it a function. So let's have a look at this. Define f from the domain, the set of all x between -1 and 1 inclusive, that's what this says here, to the real numbers. Okay, so it sends this little interval to the real numbers explicitly by this rule. X is sent to minus the square root of 1 minus x squared. Now, if x is between -1 and 1, then what we have inside the square root here is positive or 0. So this is okay. And now if we plot it, it looks like this, right? So what we've done is taken the circle and thrown away the top half. Okay, so now any vertical line that passes through this curve has exactly one intersection with the curve. All right, so now we have a function. Okay, so we'll generally focus on functions over the set of real numbers in calculus, but functions can be defined on other sets too. For example, if f sends integers to integers, so that's z for Zahlen, or number, integers, these are the whole numbers, by f of x is 2x, so this takes an integer x and it sends it to the even integer 2x. So it just doubles an integer x. Okay, so we can show that that is a function. Second page, or third page, is it? Okay, page 3. So to begin our brief introduction of univariate calculus, we must first learn what a limit is. The limit as x approaches a of the function f of x denoted, so here we have lim for limit, and then underneath that, or as a subscript on the right hand side, you could put x long arrow a. So as x approaches a of f of x. So this is how you write that mathematically. The limit as x approaches a. This is a number that is obtained for x close to a, but not necessarily equal to a. Okay, so according to Spivak, we've got the following definition of a limit. So this is an example of an epsilon delta limit. Okay, now this is pretty much background only because typically engineers would shy away from this type of definition. This is more for mathematics students. But let's talk about it. Okay, it'll be brief. I'll give you one example and then we'll move on from it. The function f approaches the limit L near a means for every epsilon greater than 0, so for every positive epsilon, there is some positive delta such that for all x, if the absolute value of x minus a is positive but less than delta, then the absolute value of f of x minus L is less than epsilon. But this can be hard to visualize, so to visualize that, I would suggest that you go ahead and look at the figure on the next page, figure 5. Right, so here we have in height f of x, right, where the dot is, and then up here the dashed line is f of x plus epsilon, and then down there f of x minus epsilon. So for every positive real epsilon, we can always find a delta that boxes this in. Okay, so that's our definition of the function approaching the limit L. And so L would be where we have f of x there. So we can always find a delta that boxes that in. All right, so anyway, back to this. An important notion in the study of calculus of functions is that of continuity. A function f sending x to y is said to be continuous at a in x if the limit as x approaches a of f of x is equal to f of a. So the values near f of x as x approaches a are equal to f of a. So if that holds, f is continuous on x if for all a in x, f is continuous at x. In other words, when you sketch the curve y equals f of x, you never need to lift your pen to do so. All right, now have a look at this figure. So here we've got the cubic function f of x is x cubed plus 5x squared minus 2, shown here. All right, so if you were to sketch this, you wouldn't need to lift your pen up to be able to do the whole thing, even though, you know, this keeps going on in both directions, but you wouldn't need to lift your pen up to draw that. So this function here is continuous on the set of all real numbers because it's continuous at every point in the domain. All right, example 1.3. Let's look at an example of a function that is not continuous. Let f be a map from the real numbers to the real numbers given by f of x is equal to x squared plus 3 if x is less than or equal to 2, and 3x plus 7 if x is greater than 2. So I've plotted that right here. And why don't I, while I'm at it, show you how to plot that yourself. Okay, so I'll just start off writing plot. Now I don't need contour plot because this is a function. All right, so now inside there, because I've got this if, I'll just put in this conditional if. So if x is less than or equal to 2, then it's x squared plus 3. Okay, otherwise we would have to have x is greater than 2, so in that case 3x plus 7. Right, now let's plot this as x goes from -6 to 5, as we have in the diagram. Okay, so there we go. There's a little plot of it. So you can see in this plot, well, if I were to sketch this by hand, I would have to lift my pen up to keep going right here when I get to 2. I have to lift my pen up at 2 and keep going up higher. All right, so the function f is not continuous since the limit as x approaches 2 from below. Now notice that little superscript here, the minus sign above and to the right of the 2. That is, we say, from below. Now that means really coming from the left. So approaching 2 from the left, where do we end up? Well, we end up right here at 7, right? The height is 7 of this function. Now coming from above, superscript plus, that means we're coming from this direction towards 2. Coming from this direction towards 2, we don't end up at 7, we actually end up at 13. Okay, so limit as x goes to 2 from below of f of x is equal to, now we just take the definition that we have here because this is from below. So it's the limit as x goes to 2 of x squared plus 3. And then now we can see we simply sub in the 2 and we've got 2 squared plus 3, which is 4 plus 3 is 7. Now from above, the limit as x goes to 2 superscript plus of f of x. All right, since now we're coming from the right hand side, well, this is where that it's defined on the right of 2. So this is the limit as x approaches 2 of 3x plus 2. Okay, yeah. And so what do we have? We've got 3 times 2 plus 2, which is 8. So why do I have 13 there? Yeah, I don't see why I've got 13 there. So let's just cross that out and put 8. Okay, anyway, 7 is not equal to 8. So the limit from below and from above, they're not equal. So the limit as x approaches 2 does not even exist, right? They've got to be the same on the left and on the right, or from below and from above. So that limit doesn't exist, and therefore we cannot have the limit as x approaches 2 of f of x being equal to f of 2. Now incidentally, f of 2 is equal to, so it's defined here because we've got the equal sign on the top bit, right? So it is 2 squared plus 3, which is 7. Okay, but the limit as x approaches 2 does not even exist. Okay, so back to this diagram that pertains to the previous definition. So here, for all epsilon positive, we can always find delta positive such that absolute value of x minus a is between 0 and delta. This implies that absolute value of f of x minus L is less than epsilon. So we can always find delta so that L is boxed into this region here. Okay, definition 4. Let f be a map from R to R, or a function from real numbers to real numbers. F is continuous at A if for all epsilon greater than 0, there's a positive delta such that f of x minus f of a is less than epsilon whenever x minus a absolute value is less than delta. So in the next example, we'll use this definition. It's pretty tricky to think about at first, But the example is fairly straightforward. All right, so let's have a look. So to rephrase this, and I'm going to put this paper up here for reference, if I can fit it up. Okay. Possibly like that for now. Yes. To rephrase this definition, the part between the vertical dashed lines in figure 5 must be all within the horizontal dashed lines to be called continuous. Example 1.4. Consider f from real numbers to real numbers given by f of x is 3x plus 2. So a simple line of slope 3 and intercept 2. Use the epsilon delta definition to show that f is continuous on the real numbers. Okay, so what we want to do here is say, given any positive real number epsilon, so positive, greater than 0, choose delta equal to 1/3 epsilon. Okay, now that choice is inspired by that 3 up there, incidentally, but you'll see how it works if you do a few examples like this. Okay, so notice here that since epsilon is positive, delta has to be positive too. Right? If you put in a positive number here, then 1/3 of that positive number is also positive. So if epsilon's positive, then delta's positive. Now this is part of the we can always find part of that. So there is delta, so that should be read as there we can always find delta. And I say that because it's easier to think about it that way. All right, so moving on. Now absolute value of x, f of x minus f of a is equal to, so we've got 3x plus 2 minus, now f of a is just 3a plus 2, so subtracting that we've got 3 minus 3a minus 2. All right, so we have this. Now let's simplify this. So that's absolute value of 3x minus 3a because the 2's vanish. And now there is a common 3 there. 3 is positive, so we can pull that outside of the absolute value and say that this is less than, so this is less than 3 times delta whenever absolute value of x minus a is less than delta. Okay, since we chose delta equal to 1/3 epsilon, what we see then is that absolute value of f of x minus f of a is less than, let's see, what is 3 times 1/3 epsilon? So that's just epsilon itself. And we're done, right? So we have established that the absolute value of f of x minus f of a is less than epsilon whenever x minus a is less than delta. All right, so this is an example of an epsilon delta demonstration that the linear function 3x plus 2 is continuous on the real numbers. All right, but we won't much use the epsilon delta definitions from here on. It's just something that I feel as a math student you should see once, because this is the basis for mathematical analysis. Okay, a very important concept in calculus is the derivative of a function. If f of x is a function of x, then the first derivative of f of x is defined as f dash of x is the limit as h approaches 0 of 1 on h times f of x plus h minus f of x. So see figure 6, that's on the next page. So let's have a little look. So here in figure 6 we have x. Now here is f of x This is x plus h. Up here is f of x plus h. So what we're doing then is constructing the slope of this line segment, right? But then we're taking h as it gets closer and closer to 0. So imagine this as it approaches this x comma f of x point, right? So then what would happen is that slope of the secant or line segment would approach the slope of the function at that x value. Right, so this is the definition of the first derivative. It's the limit as h approaches 0 of 1 on h f of x plus h minus f of x. Okay, so let's use this definition here to calculate the derivative of this function. It's a simple quadratic function. So we have f dash of x is equal to the limit as h approaches 0 of 1 on h f of x plus h minus f of x. Okay, now let's sub in f of x plus h. So what we're doing is we're replacing all of the x's with x plus h. So we still need to write limit as h goes to 0, 1 on h. Now we have x plus h squared plus 3 times x plus h minus 6. And then subtracting f of x, well, f of x is just right here. So we subtract x squared, 3x, and then minus 6 is plus 6. Okay, now we want to simplify this. So simplifying this would mean expanding these brackets out and canceling identical terms. So let's go ahead and do that. I still need to write limit here. Limit as h goes to 0, 1 on h. Now the expansion of x plus h all squared is x squared plus 2hx plus h squared. The expansion of 3 times x plus h is 3x plus 3h. And we have minus 6. We have minus x squared. We have minus 3x. And we have plus 6. Notice I've lined them up to show that they're going to vanish in the next step, right? Okay, so next we want to make those things that vanish vanish. So limit as h goes to 0, 1 on h. So the x squareds vanish. We have left over 2hx plus h squared. 3x's vanish. Then we have 3h, and the 6's vanish. Okay, we're nearly done here. What we want to do next is factorize the h out because we can cancel that. So factoring that out of this expression and canceling that with the 1 on h, well, what we have left over, and we still need to write limit as h goes to 0 here at this point. So what we have left over is 2x plus h plus 3. Okay, and in the last step, now replace the h with 0. So we have, and you don't need to write limit when you've done this. So 2x plus 0 plus 3, and of course that is 2x plus 3. Okay, so this is using the definition of the derivative to calculate that derivative. But of course we have rules for this, right? Which I hope you remember. And here I've got a little list of those important rules. So if c is a constant, then the derivative of constant times y with respect to x is the constant times the derivative. So this is Leibniz's notation, and this is Newton's notation. Now, I will generally use Newton's notation, but I understand that a lot of you have learned your one variable calculus in terms of Newton's notation, right? So that's fine too. But I mean, the advantage in my mind of using Leibniz's notation is that it's a good aid to memory for the rules of integration in particular. All right, so that's the reason why I generally use Leibniz's notation over Newton's, but they both have advantages and disadvantages in their use. Okay, so basically you can move a constant through the differential operator d on dx. The derivative of a sum is the sum of the derivatives. Right, so this is Leibniz's notation, and in terms of Newton's notation, you would just apply the dash to each one. So just as simple here. Derivatives to remember. The derivative of x to the power of n is n times x to the power of n minus 1. The derivative of e to the x is e to the x. The derivative of sine is cos. The derivative of cos is minus sine. So these are really important derivatives to remember. Now for each of these, you could use the definition of the derivative to do it, but you'd have to use some other rules. Like for example, for sine, I think you might have to use what's called the squeeze theorem. Okay, product rule of differentiation. The derivative of a product is the sum of two things. So the derivative of uv with respect to x is v times du on dx plus u times dv on dx. So I just pull out one, multiply by the derivative of the other, and then swap around. That's the way I talk about this. All right, now in Newton's notation, this is the derivative of the product of two functions f and g is g times f dash of x plus f times g dash of x. Again, simple. Okay, the quotient rule of differentiation. The derivative of the quotient u divided by v is 1 on v squared, v du on dx minus u dv on dx. Now notice that I've written it in a way that looks like this, so that this would be, or this would be an aid to memory to this, right? That's why I put the v first in this one, just to help remember with the quotient rule. Okay, now in Newton's language, so f over g differentiated is 1 on g squared, g f dash minus f g dash. Chain rule of differentiation in one variable. dy on dx is dy on du times du on dx. Now in aid to memory, if you were to think of these as fractions, but they're not fractions, the du's would cancel and this would be left with dy on du, right? So that's an aid to memory for the rule of differentiation, right? And so in this sense, Leibniz's notation is useful here because it does behave like fractions in many ways. Okay, now in Leibniz's notation, f of g of x differentiated is f dash of g of x times g dash of x. Let's look at an example. So we'll differentiate this function, and I'll use I'll use Leibniz's notation to differentiate it, but I'll mix it a little bit, right? Because to minimize what I have to write, I'll go f dash of x is equal to, and then I'll swap notations because it's convenient to do so. D on dx, 9x to the 6th plus 4x squared plus sine of x. I want to differentiate this. Okay, now I can split this up. So what I'm going to use is the fact that the derivative of a sum is the sum of the derivative. So that's second one. So we have d on dx, 9x to the 6th plus d on dx, 4x squared plus d on dx of sine x. Okay, so that's using that second rule up there. Now next, let's use the first one because the derivative of a constant times a function is that constant times the derivative of a function. So we've got 9 times the derivative of x to the 6th plus 4 times the derivative of x squared, and then the derivative of sine is just cos, right? So that was the one to remember up here. So we'll just put plus cos of x. Okay, good. Now we can use the rule that the derivative of x to the power of n is n times x to the n minus 1. Bring the 6 down, subtract 1 from the exponent. So we've got 9 times 6 times x to the power of 5 plus 4 times 2 times x to the power of 1, and then we still have cos of x. Okay, simplifying this, we've got 54 x to the 5th plus 8x plus cos of x. All right, now let's check this with Mathematica. So what I want to do here is use an uppercase D, set it up like this, and then I'll just write my function in here. So 9x to the power of 6 plus 4x to the power of 2 plus sine of x. Okay, shift and enter. So I've got 8x, that's this, 54x to the 5th plus cos of x. Okay. And incidentally, if you wanted to use Wolfram Alpha here, what you would do, because you can call this from within Mathematica, press 2 equals at the start of a cell, and then you can just write in plain English, differentiate 9x to the power of 6 plus 4x to the power of 2 plus sine of x. And you can even misuse the syntax, right? You see how I put a round bracket in there? Now press shift enter. This will call on Wolfram Alpha, and it will even show you step by steps. Okay, so here we go. It's called on that. It's still running, but we can see some of the output. Okay, there's the mouse. All right, so I could, and it shows you lots of irrelevant things too, right? So I can see step-by-step solution. Okay, it'll open that up. And it basically shows you what I've done here by hand, but no video, all right? So, okay. So now what I'll do is I'll cut this and carry on. Example 1.7. Use the appropriate rules of differentiation to calculate f dash of x for the function given by 2e to the 3x squared cos x. All right, well, we can see it's a product of two things, so we're going to use the product rule, but we can see that one of the multiplicons, or things being multiplied, is a function of something else, so we'll also need the chain rule. All right, so f dash of x is equal to the derivative of 2e to the 3x squared cos of x. Okay, so first move the 2 out. So we have 2, and now we'll use the product rule. So I want to pull one of these out. So cos of x multiply by the derivative of the other one, and then we swap around. But since we pulled out the 2 first, we'll put a bracket in here, and then we have plus e to the 3x squared times the derivative with respect to x of cos of x. Okay, so we've used the product rule. Let's say by product rule. You don't have to write this. Might help when you read it back. All right, so next, now this is easy enough. We can finish this part quite easily because the derivative of cos is minus sine. But this part here requires the chain rule. So if you want to say, set out, let u equal 3x squared, you can, right? So I'm going to write this. So we've got cos of x, and then we need the chain rule for this part. So that's d e to the 3x squared, put a bracket around that, with respect to 3x squared. Put a bracket around this, and then multiply by derivative of 3x squared with respect to x. Okay, so this is the chain rule. You see, in aid to memory, it looks like if these were fractions, but they're not, these would cancel and we would have exactly this, right? So that reminds you, yes, I've got the right rule. Okay, so let's do the rest of this. Plus, now derivative of cos of x is minus sine, so we'll put minus e to the 3x squared sine of x. All right, now let's do this part. So here we've really set out u equals 3x squared. Okay, so let's rewrite this then. What this is, f dash x is 2 outside of cos x. Then we have d e to the u on du multiplied by this derivative, but that derivative is easy, right? So the derivative of 3x squared is 3 times 2 is 6, x to the 1. So times 6x. And then here we just copy this down. Because we've already calculated that little piece. Okay, now the derivative of e to the u with respect to u is just e to the u. So we've got 2 outside of cos x times e to the u times 6x minus e to the 3x squared sine of x. Okay, so what remains to do is sub that u back in here and then tidy it up. So we've got 2 outside of cos of x e to the 3x squared times 6x minus e to the 3x squared sine of x. Okay, we've got some things common. So let's factor out this e to the 3x squared, put it in front. So 2 e to the 3x squared outside of 6x cos of x minus sine of x. Okay, so we've expanded, simplified, and factorized, and we now have our derivative. But let's get Mathematica to check this. So I'll put in uppercase D, 2, and then I'll write exp 3x to the power of 2. And then outside that, we'll put cos of x. Whoops. Differentiating with respect to x, shift and enter. So here we get the expanded form. All right, so I probably also want to factorize that. So in front of this, I'll write factor. Okay, so do we have the same thing? Looking good, great. Okay, so you can see, this is not, I'm not going to rely on this for your assessment, right? So you won't have to know how to use this software for your assessment, but you can see it's really, really useful because you can check this, and it's so easy to get these things wrong, right? Downside is, I'm not going to let you use it on your exam, of course, because that's an in-class exam. So you really have to have these by-hand skills mastered, but by all means you can use Mathematica to check your work along the way. All right, example 1.8. Use the appropriate rules of differentiation to calculate f dash x for the function given by this. So it's a quotient of two things. All right, so let's set out, let u be equal to 4x minus 5 and v be equal to x squared minus 2x plus 4. So what we have then is f of x is u over v. All right, now we use the quotient rule for this. So by the quotient rule, f dash of x is equal to 1 on v squared, v du on dx, minus u dv on dx. Okay, what's the derivative of u? Well, it's just 4. You can see that. So I'm going to leave the v squared in place because if you had wrote that out, like you'd be rewriting that a lot, right? So just keep that for now. And I'll keep this v here for now too, but the derivative of u, just looking at that with respect to x, is 4. And then minus u times the derivative of v with respect to x. Well, we can do this in our head too. The derivative of v with respect to x is 2x minus 2. Put a bracket in, so 2x minus 2. Okay, so now we want to do some expansion. So what is 4 times v? Let's keep the 1 on v squared here as is for now. But 4v is 4x squared minus 8x plus 16. Okay, u times, now u is, well, let's put in u here, 2x minus 2. Okay, now we've got to expand this. Okay, so expanding this, 4x times 2x is 8x squared. But we'll do this in the next line. So 1 on v squared. So we have 4x squared minus 8x plus 16. And then minus, we'll keep the bracket in for now. Okay, so 8x squared is this with this. Then this with this gives us minus 8x. Okay, then this with this is minus 10x. And then this with this is plus 10. Okay, now we've got to put the minus sign on each of these and simplify. So for now, since we've got more work to do, keep the 1 on v squared as is. So we've got 4x squared minus 8x plus 16. And then here that's minus 8x squared, so we'll write that underneath. And then this is plus 8x. And then this is plus 10x. And then minus 10. Okay, there we go. So now we can simplify. And since it's going to be simplified in this step, now let's replace the v with x squared minus 2x plus 4. So 1 over x squared minus 2x plus 4. Brackets, we've got minus 4x squared for the difference of these two. These vanish, but then we're left with plus 10x. 16 minus 10 is 6. Okay, now we could factorize a 2 out of this, and possibly even more, right? But I'd say that's good enough. Now let's see what Mathematica has to say about this. So let's differentiate something divided by something with respect to x. Okay, that numerator is 4x minus 5. The denominator is x squared minus 2x plus 4. Okay, so it gives us a rather ugly sum of two fractions, so we might want to write factor in front of that. Okay, so that looks better, and so it tells us to tidy this up. We've got a little bit more work to do here, right? So this looks probably like this, right? So let's pull the 2 out. And in fact, let's pull a minus 2 out so we have a leading coefficient of positive. So minus 2, and then what remains when we factored out a minus 2 is 2x squared minus 5x minus 3. Okay, and I've forgotten the square there, incidentally. All right, now that numerator factors into a product of two linear factors with integer coefficients, incidentally. And so we've got minus 2. So let's put a 2x and then another bracket and then a single x. Okay, we've got to work out what goes there and there, but we already know according to what Mathematica has given us. All right, so what do I need? Now, the divisors of 3 are 1 and 3. So I could have a 1 here and a 3 there, or a 3 there and a 1 there. So if I put a 3 here, then the product of 2 and 3 is 6. And if I put a 1 there, well, yeah, the difference gives me 5. So that's what we want. 1 and the 3. Now to look for the signs. So the bigger one, we need to be negative so that it comes out minus 6x, and the smaller one plus 1, so that we get minus 5x there. All right, is that what Mathematica gave us? Yes. Great, so here's the fully factorized and simplified form. Okay, a function is f of f sending x to y is said to be differentiable at x equals a if the derivative f dash x exists. A function f is said to be differentiable if the derivative exists for all x in the set x. So this is differentiable at a. This is differentiable on the entire domain. So it has to be differentiable at every point in that domain. All right, a useful consequence of the definition is the following statement. If the function f is differentiable at x equals a, then f dash is continuous on, or continuous at a. I should say at a. Example 1.9. Consider the piecewise function given by f of x is x minus 1 absolute value if x is not equal to 1 and a if x is equal to 1. For which values of a is f of x continuous at x equals 1, and for these values of a is f of x differentiable at x equals 1. All right, so you also want to have a picture of this. So first, let's use the definition of continuous. So for f continuous, at a, we would need the limit as x approaches 1, because this is where things change. All right, f of x to be equal to f of 1. Right, but since this is a piecewise function, we have to check the limit from below and from above to even make sure that that limit exists. So we need this to exist. So the limit as x approaches 1 from below of f of x, well, so that is then equal to the limit as x approaches 1 from below of x minus 1 absolute value. And so here, since it's from below, think, just in brackets here, think e.g. x equals something slightly less than 1. So it's from below, right? So 0.99, for example. All right, so what does this look like? 0.99 minus 1 is minus 0.01, but then we have the absolute value, which gives plus 0.01, right? So this is really close to 0, right? And so if you have 0.9999999, you get something very small but positive, right? So this limit is equal to 0. Okay, now from above, it's the same story. The limit as x goes to 1 from above of f of x, it's the limit x goes to 1 from above, absolute value of x minus 1. Same story, we get 0 because here we're thinking, for example, of something like 1.01. So as x approaches 1 from something on the right, okay, going towards 1. So again, we get 0. These two match, so that limit does exist. So the limit as x goes to 1 of f of x is equal to 0 because these two match. So this exists. Now, is this equal to f of 1, which is a? Okay, if this function is continuous, then yes, it would be. So since f is continuous, we have to have a equals 0. Okay, so then that tells us that f of x is defined absolute value x minus 1 if x is not equal to 1, and 0 if x is equal to 1. Okay, so now that we have that, let's just sketch this. So here's 1. On the right hand side it looks like this. On the left hand side it looks like this, because we have an absolute value here. Alright, so then, is this differentiable at x equals 1? Well, the limit as x approaches 1 from below of f dash of x is equal to the limit as x approaches 1 from below of, now, what is that? That's got a slope of -1 there on that side. All right, and so this limit is just -1. Right, now if you take this from the other side towards there, you've got the limit as x approaches 1 from above f dash of x, which is +1. Okay, these are not equal. So here we don't have a differentiable function. All right, so we'll just write up here because this is the only space we have. So f is continuous at x equals 1. Here a is equal to 0, but f is not differentiable. At x equals 1. All right, because this derivative or slope is ambiguous there at this point. On the right hand side of it, it's +1. On the left hand side, it's -1. But what is it here? Well, it's ambiguous. It's ambiguous at x equals 1. So for that reason, this function is not differentiable when at x equals 1. So it's continuous but not differentiable. All right, now remember what the theorem said. If the function is differentiable, then it's continuous, right? But not necessarily the other way around, right? So the converse of this is false in general.